Hi there, I'm Scott Lowe with ActualTech Media, and I'm here today with Josh Goldenhar from Excelero. Josh is the VP for Customer Success for the company, and we're here to talk about NVMe.
Hi, Scott. Yes, we are. Thanks a lot.
And thank you for having us in your offices today.
Hey, no problem. It's a pleasure.
So tell us about NVMe and what Excelero is doing to bring more NVMe goodness to the world.
Well, NVMe is really somewhat understood as a misnomer by a lot of people. NVMe think it's a particular media type. They relate it to flash and being really fast. What makes it really fast is actually NVMe is a protocol. It's an API for the computer actually talking to the drives. So it's highly optimized. It's made for flash. And because of this, it makes traditional NAND, the same kind of flash drives, by the way, the same kind of NAND and media that's on SAS and SATA flash drives. So the NAND is the same, but the controller is new, and the API is streamlined, and it's highly, highly parallel. So in fact, it matches RDMA type operations that have been in use for years and years in HPC and other areas of very high performance compute and networking. So the great thing about NVMe is that if you can parallelize your load, if you can do a lot of operations at once, it goes really, really fast. It's very low latency because it's right on the same bus as the CPU in a computer. So you're not going through another bridge. That reduces latency, but mainly it's the API itself that makes it very, very fast. So it's not really a new media type. It's the actual physical media is the same, but it's a new way to access that really lends itself to parallel operations.
Now, I see a lot of press around NVMe drives and things like that, and I understand that they're trying to make a nuance, that they have a different interface,
Right.
a different protocol. But a lot of what we see, in a traditional flash has been really retrofitted SAS and SATA that have some serious limitations that NVMe overcomes.
Yes.
What are some of the things that NVMe is doing that really build on, or really take SAS and SATA out of the equation and bring things to the next level?
Well, a lot of it is a bit of what I referred to, in that this new API allows for a way of interacting with the media that wasn't possible before. So for example, on a SATA drive, you essentially could do one operation at a time. So even though a SATA drive might have the same amount of NAND and might be on a high-speed bus, you simply can't do as many parallel operations. So it tends to be limited to about 500 megabytes per second for a single drive. Whereas on NVMe, on a by-4 interface NVMe, these things go about 3 to 3.2 gigabytes per second from a single drive. So that really opens up the bandwidth. Now, the API is very, very efficient, and you have new controllers on these devices. So the latency of every individual transaction actually goes way down. So this is what makes it seem like, and it is very exciting, by the way. It's this media that sits on a computer, and it's right next to the CPU, so you're not going through some other bridge. Traditionally on SAS or SATA, you go through a SAS or SATA controller. So the bus talks to the controller, and then that controller in turn talks to the drives. So you've eliminated a hop. Mm-hmm. It's direct communication. It's very low latency. And it's essentially like driving on the freeway if you have a 6-lane freeway and nobody else is on it. That's basically what it's like.
So what has Excelero actually brought to market?
So Excelero early on, our 3 technical founders, realized that what was really exciting about NVMe architecture and the NVMe API is that it directly matched the kind of programming you do in RDMA. And for folks that don't know, RDMA is simply a network style of communication that offloads what's traditionally done by the CPU into the hardware NIC itself, and it avoids copies. This gets kind of technical. But basically, instead of, for instance, me talking to you and you relaying a conversation to someone else, to a third party, I'm able, over the network, for 2 computers to directly exchange information to each other's memory. Mm-hmm. Whereas something like a protocol like traditional TCP/IP makes a copy of memory into another buffer, sends it over the network into another buffer, and then makes another copy. So it adds a lot of latency, and it's generally the CPUs that are doing that work of moving all that data. In RDMA, they streamline all this, and it's offloaded to hardware. Mm-hmm. Now, we don't want to go too far down that rabbit hole, but suffice it to say, it's very, very offloaded, very, very quick to exchange information between 2 computers. And the way you program these things with something called verbs was borrowed, let's say, for the NVMe protocol. So they're almost a one-to-one match. What early on our founders thought was, you know what, this API for NVMe is so close to RDMA, and this was long before NVMe over Fabric was even thought of or anybody was talking about making it into a standard. They said, I bet we can access NVMe, and this was in 2014, early in 2014, we bet we can access NVMe remotely over RDMA from another computer at essentially the same speed. And that was the formation, the kernel of the idea that eventually formed the company, which was let's access this media across a network like NVMe over Fabric. But unlike NVMe over Fabric, which is just a protocol, we not only have very, very low latency, high speed access to that remote media, but we completely virtualize it out to seem like a virtual all-flash array, or what we're calling software SAN. That we're borrowing that term. But software SAN is basically, it's SAN-like functionality, only in software, or server SAN, meaning you take commodity servers, you run our software, and it functions like a SAN. You get logical volumes that are using NVMe as the back-end media. Operationally, you can, if you want to, you can consolidate your media into single servers, so it's very operationally efficient. And instead of managing, for instance, 200 individual drives, it's a single pool that you carve logical volumes out of whatever size you want, with protection, and therefore you get a virtual SAN.
You know, when you talk about all this, it becomes clear that there's new workloads that really require this sort of capability. And we're talking about AI and big data and analytics that really data, I almost hate the phrase data is currency, but it's a real thing. And he who has the data has the power. And only if you can do something with it. So when you start looking at data capabilities, data analytics, and AI, what is Excelero helping do for customers on those fronts?
So what we're really doing is helping preserve workflows. So you can look at it in this manner. Almost a part of your question is also, where is this applicable? Is it applicable for AI? And really, what we have to look at, and what we look at when we're trying to sell, is would someone benefit from using local NVMe? And or have they made that decision? They said, you know what, the only way I can get the performance I need is if I go ahead and I put that NVMe flash locally. So if they've made that decision, generally what they do is they break their workflows. So in AI, it's very, very common to bring in a very large data set. Whether this is your autonomous fleet of cars that have been running and you've collected lots of sensor data and you want to see how the cars performed in simulation versus the actual data. Or maybe you have an application that you want to automatically identify images. You want to be able to say, you know, this is a beer glass. So you might bring in 100,000 images of beer glasses from different angles, different lighting, et cetera. So the data sets tend to be very, very large, up to multiple terabytes or tens of terabytes. The accepted method for AI is to take your systems that very often have GPUs installed. And the only way you can process this fast enough, at least that was the thought, was to put NVMe media inside the servers that have the GPUs. Now, the problem here is that it's twofold. One is that you can't fit a multi-10 terabyte data set into one system. And even if you could, it doesn't matter. It can't process all that data. It would take too long. So you want to spread the data set over multiple systems. You have to know how to divide it. You take time to divide it up. You copy then over to your media. And then where this is flash we're talking about. At the end of the day, whether it's NVMe or if it's SAS or SATA, flash wears out. So if you have a centralized data pool and you have to copy it local and you process it and then you erase it and you wash, rinse, repeat, it means you're constantly writing over and you're trying to fill it up generally. So you're doing what might be multiple writes per day. So you're going to require very high write endurance media. So it's going to be costly. You're going to take the time to copy it. You're going to process it. You're going to throw it away. This is a broken workflow.
Right.
What people would really like is they'd like to have that centralized pool and just simply access it from the GPU servers and analyze it. And long story short, that's what we enable. We enable you to access that data at speeds as if it's local. Same latencies, same bandwidth, sometimes actually oddly lower latencies. As if it's local, you process it, you don't have to copy, so you get very, very efficient use of your flash media, and you're not constantly rotating it as if you were locally. Very
cool. Now, before this video, we talked about some wins that Accelero's seen in the recent past here, or right before this. What are some of who are some of your customers, and what are they doing with Excelero?
So we have a varied amount of customers, which is actually, I think, unique in that we don't necessarily focus on one particular vertical. So we have smaller customers that are in traditional FSI, especially hedge funds, doing back testing, things you'd think about that are either high bandwidth or low latency or both. Not very exciting though. We have some in the banking industry. So we do have a very large bank that's using us, and we're happy about that. But the more interesting ones, of course, are the ones you can talk about.
Right.
So most recently, what I was talking about a lot, because we were just at International Supercomputing in Germany, was our SciNet use case. So SciNet is part of the University of Toronto, and they're using us for a burst buffer. So underneath a file system we like very much, IBM Spectrum scale, we are taking the place of basically a traditional array. So rather than have an external array, we're allowing that customer to use standard servers, in this case provided by Lenovo. It's a relatively small number of servers, and it creates a burst buffer, which is a place that you can do very, very high bandwidth writes very quickly. So they're using it there for burst buffer, and then in their compute nodes, they also have some usage in a general purpose sense where they needed high random IOPS. So it's unique in that we present this solution that acts like a SAN, extremely high performance, high bandwidth, but it can also be high random IOP, either reads or writes. So that's what's unique. So pairing the two together is used for traditional burst buffer as well as some analytic loads and some MPI style computing at the University of Toronto. Now this is an HPC use case. People might say, oh yeah, it's really, really high performance, and tell me something I know. So one of the most exciting we have is a partnership with Technicolor. And I say partnership because while they are a customer, and we announced them as a customer at this last NAB show in Las Vegas, we've really worked together with them to make the best solution possible for what they're doing. And Technicolor is doing post-production color correction. So for folks out there who say, what in the world is that? Basically, when a movie gets completed, it goes off to a shop like Technicolor for post-production. That is, it's post all the filming and the production. And they make corrections to the color, to the lighting. Maybe they put in some visual effects. And this is all done by editors who have to work with very large files. As resolutions go up on how movies are captured, these folks are actually dealing with bandwidth that previously was only thought about in loads like HPC. So that's why there's actually a tie here. You have editors who are running workstations that have to do sometimes tens of gigabytes per second. It's over 10 gigabytes, not gigabit. Right. Over 10 gigabyte per second of bandwidth. And this is when you have multiple 4K streams. Some source footage is coming in at 8K. And when you do overlay work, sometimes you need simultaneous streams in a film. So these can be very, very intensive. Technicolor, like so many other companies, was caught in this kind of treadmill cycle of upgrading their fiber channel. And we worked with them specifically to say, how can we make this better? And we came up with what we call the NEK solution. What this means is the resolution of the video can be NEK. People have heard about 2K, right, 4K video. Well, we're saying, actually, this was coined by the customer, that they can do NEK with us. And what they meant by that was, rather than upgrading from fiber channel 8 or fiber channel 16, they just said, we're not going to upgrade fiber channel anymore. We're tossing it out. They're using 100 gigabit Ethernet on the servers, and whatever speed they want on the workstations, from 25 gigabit up to 100, or even multiple 100 gigabit links. This is all about half the cost of fiber channel 32, but 3 times the bandwidth. And that's where we get this NEK, because we provide a scalable solution that even if they start at a certain resolution and bandwidth today, they can always just add off-the-shelf servers and more NVMe to make it a very, very fast system, very scalable for whatever NEK video they want to get to. And so that's why they are both a customer and a partner. We're very happy to be working with them. They've been very terrific. And what we're solving is just what I described before. They were copying data onto the workstations, which meant all workflow was serialized. Right. That editor could work on it, and nobody else had any access to that, waited until they were done, where they copied it back. If they had a failure on that workstation while it was on the workstation, they may lose all the work that they were doing temporarily. And lastly, of course, we all know that the studios are very, very sensitive to movies making their way on the internet. So this actually gives them a method to keep everything a bit more secure, because the movie is on centralized and controlled servers. So all these things together mean that they have speeds that are sometimes better than they could get with local media. Latency is very, very low because of NVMe underneath and NVMesh accessing that at basically local latencies. And this gives them the ability to do their work faster in a more natural way, preserving their workflows. And we know that they're working on currently their 3rd feature film. We can't say which ones they are, but if you go to the movies and you see Technicolor at the end for any movies now, there's a good chance that's used on Excelero NVMesh.
Very good. Josh, thank you very much for this overview of the company and for that really interesting insight into some of the use cases.
Great. No, it's been a pleasure. Thank you.
And thank you to our audience for watching this Roadcast video.